Okay, growth curves. Explain the different population growth patterns, logistic and exponential, and open and closed populations. Okay, nearly all populations grow exponentially as long as there is enough space, uh, mates, and food, and so on and so forth. Okay, so we've got two different types of curves here. We've got the J curve, and we're going to compare it to the S curve, also known as the logistic or restricted growth curve. J, normally followed by a sharp decline in population, which may rise rapidly again. So the J curve is cyclic in nature. Exponential, unrestricted growth, okay? This would be characteristic of mosquitoes. They are cyclic in nature. They come out in the spring, they die in the fall, they crash, and then poof, they're back at it. This would not be characteristic of mosquitoes. The carrying capacity is reached, and then populations will tend to fluctuate above and below that carrying capacity. So we have different phases of this: a slow adjustment phase, an exponential phase, and then we get this phase where we have environmental resistance pushing down and keeping a population in check. So this would be our bears, for example, not mosquitoes. This would be R selected, high biotic potential. This would be K selected because it tends to fluctuate above and below a carrying capacity. So as a population increases in size, limiting factors such as disease, predation, reduce the amount of energy that's available. This causes growth rate in population. So that's just what we talked about in the last lesson. These are the factors that are going to hold a population in check from exponential to carrying capacity, unless, of course, you're things like our selected species like mosquitoes. Okay, here's our bears or our fish in the lake. Another way to look at it, so the slow adjustment phase is called the lag phase. There's the exponential phase. Things start slowing down as density dependent factors increase. And there's our carrying capacity. Fluctuates above and below a set number, K. Another way to look at it, high biotic potential, that's right, and it hits carrying capacity. Okay, now I just want to mention about closed populations, though. Closed populations is where there's no immigration or immigration. So take a look at this bacteria, for example, in this petri dish. It can't leave or enter that petri dish. So you give it lots of food, and it actually takes a while before the bacteria start increasing. It then has exponential growth. This is where the natality is greater than the mortality. But then, because of these density-dependent factors like wastes building up, the natality is going to equal the mortality. And then when there's too many wastes and not enough food, the mortality is greater than the natality, and you get the death phase. Okay, so let's go back to this R and K selected. R and K. And this is in your workbook. Unstable environment governed largely by density independent factors like floods or seasons like my mosquitoes. They're going to freeze to death. Stable environments, for K selected, density dependent interactions are going to determine yes, density dependent, determine the carrying capacity. So the organism size, well, we're going to have small, large. And you can fill this in your workbook. Low amount of energy used to each individual, high amount of energy used to make each individual. Okay, that means that there's a lot of nurturing. Bears look after their young for 2 to 3 years. Mice don't, maybe a few days, if that. Offspring, you have many mice. Okay, few mice, or in my case here, rhino. Time of maturation, very early. With K selected, there's a lot of parental care. We mentioned that with the bears, short and long. Now here's the kicker on this. The worm is probably going to be placed somewhere around here, okay? Here's some slime mold, 500 million a year, okay? 8,200, one every 5 years. So notice that this is a continuum. When we talk about RNK selected, it's on a continuum. We say that the rabbit is R selected compared to the cougar, and that these tend to be K selected species, where these are more on the R selected spectrum. Human population, as you can see here, this is a exponential growth curve, okay? And that's got to do with a number of factors, okay? Scientific advances, medicine, things where you can see the Black Death hit us right there, uh, okay? Industrial revolution, so science, medicine, agriculture has caused us to hit this. However, we probably will have a carrying capacity at about 9 billion people. And that relates to these other diagrams. So it's a good little video to watch there. Yeah, so medicine, agriculture, great. Look at these population pyramids. These are called histograms. And if we take a careful look at these histograms, let's see what they're showing. Congo, there's my males, there's my females. A high percentage of my population is in childbearing age. Lots of people. So this shows me an expanding population, okay? These people are gonna have a lot of children. This incidentally is what Nunavut looks like, okay? Which has got significant policy implications with a large expanding Aboriginal population. Look at Sweden. Well, it's got fewer children, okay? It's got a narrower base. And so this is a slower growth. Negative growth, these folks that are high childbearing populations, here's my childbearing population, are not having many children. So we have now negative growth. So Germany is only getting its population um, increased or stabilized with immigration. Okay, Syrian refugees, Turks, okay, and it's caused a lot of political issues right there. Okay, however, that's the reality. So the population, the general trend on planet Earth is moving this way. That is why the population will eventually level off.